This problem involves energy transfers and work done. We can therefore use the work-energy principle to solve it. We first need to identify the initial and final situations. The initial situation is the release point 3 meters above the car roof. The final situation is when the can is finally stopped on top of the car roof. For each of these situations, we now need to identify what the energies are. So what is the total mechanical energy initially, and what is the total mechanical energy finally? The total mechanical energies are the sum of the kinetic and potential energies, as there are no elastic energies involved in this case. The initial kinetic energy is given by half mv squared, and that is 0 because the object is released from rest. The final kinetic energy in this case is also given by half mv squared, which is also 0. And that is because the can is finally at rest. The final situation is considered when the can is at rest. The final gravitational potential energy is given by the equation mg delta H, and that is also going to be taken to be 0 because it's the lowest point. However, the initial gravitational potential energy is not 0, and that is mg times the height change. So the height change was given by the question to be 3 meters. We can therefore quantify that as the mass, which is given by the question as 250 grams. That means it's 0.250 kilograms, multiplied by g, which we will approximate to 10, multiplied by the height, which is 3 meters. This will give us a value of 7.5 joules. The work that was done to stop the body was the force exerted by the roof of the car, which is 1,500 newtons, multiplied by the distance that it acted for, which we will call unknown d, let's say in this case, and the work done can be quantified now as 1,500 times d. So to summarize so far, we've calculated the initial mechanical energy, total mechanical energy. We've calculated the final total mechanical energy to be 0, and we've also calculated the work done. So we're now ready to substitute into our work energy equation. So the total mechanical energy initially we said is 7.5 joules plus the work done, which is 1,500 times unknown distance d, and that is equal to the total mechanical energy finally, which is also 0. Now we should say here that the displacement downwards of 3 meters is considered positive. The distance moved downwards, the dent in other words, is also considered positive d. So the force, since it's acting upwards, must be considered negative. So all this here must be added to minus 1,500 d. Rearranging this equation, we have 7.5 joules equals 1,500 d, and therefore d is equal to 7.5 divided by 1,500, and that gives us a very small number. But of course, it has the units of meters.